Every night, the evidence is already above us. The moon looks ancient, silent, permanent. Nothing about it suggests catastrophe. And yet modern science reached a very different conclusion. Not because someone imagined a better story. Because the moon kept failing every test scientists expected it to pass. This documentary follows that investigation. By the end, we are going to answer one question. Why do many planetary scientists now believe the moon is the surviving physical evidence of the single most violent event in Earth's history? Not because of one discovery. Because every independent line of evidence kept pointing to the same impossible conclusion. We will follow that evidence exactly as it appeared. And we will stop where the evidence stops. The investigation begins with something surprisingly simple. Before anyone analyzed a single lunar rock, before anyone proposed a giant collision, the moon already looked wrong. If the moon were simply a smaller version of Earth, its structure should look familiar. It doesn't. For its size, the moon is unusually light. Its metallic core is remarkably small. Most of it is made of rock. Not the balanced mixture of rock and iron that built Earth. At first, none of those measurements seem extraordinary. Any one of them might have been dismissed. But they refused to stay alone. Gravity measurements revealed the same picture beneath the surface. The moon was not built like a miniature planet. It looked strangely similar to Earth's rocky exterior, while missing most of the heavy metal hidden deep inside our own world. One measurement can be an accident. Several independent measurements become evidence. Without knowing anything about its origin, the investigation had already changed. The moon was no longer just the familiar object hanging above every civilization in history. It had become a planetary anomaly. And once that happened, looking at the moon was no longer enough. If the answer existed anywhere, it would have to be hidden inside the moon itself. The investigation was about to leave the night sky. It was about to enter a laboratory where scientists could finally hold the evidence in their hands. Inside climate-controlled storage, behind sealed glass and surrounded by dry nitrogen gas, small gray fragments rest in carefully labeled containers. They do not sparkle. They do not look extraordinary. Some resemble ordinary gravel collected from a dry hillside. Yet every fragment here was carried back from the moon. These samples transformed the investigation. The moon was no longer a distant object observed through telescopes. It became physical evidence that could be weighed, sliced, polished, measured, and tested. Among them are basalt fragments formed from ancient lava and pale anorthosite rocks that crystallized when the young moon was covered by a global magma ocean. Their surfaces still preserve billions of years of history because, unlike Earth's rocks, they were never altered by rain, rivers, or life. That changes what these samples can tell us. On Earth, weather constantly rewrites the geological record. On the moon, the record remained exposed in vacuum for billions of years. Each crystal preserves conditions from an era our own planet has almost completely erased. The laboratory does not begin by searching for spectacular discoveries. It begins by protecting the evidence. Technicians handle the rocks inside sealed glove boxes filled with pure nitrogen. Moisture from Earth's atmosphere is kept away. Even fingerprints are treated as contamination. Every cut, every polished surface, every prepared sample exists for one purpose: to recover information that has remained locked inside these minerals since the moon itself was young. As the investigation moves from observation to direct examination, the moon changes again. It is no longer simply an unusual world. It becomes a geological witness. These rocks are not valuable because they came from space. They are valuable because they preserve a planetary history that can still be measured atom by atom. For now, the laboratory has established one fact. Scientists possess authentic pieces of the moon, preserved well enough to reconstruct events older than almost any surviving rock on Earth. The question is no longer whether evidence exists. The question is what that evidence will reveal when its chemistry is finally examined. The first measurements do not look dramatic. There are no glowing reactions, no visible transformation, only instruments separating atoms with extraordinary precision. For planetary scientists, that precision matters because every world in the early solar system formed from material that carried its own chemical signature. Tiny differences in oxygen isotopes act like geographic fingerprints. Rocks formed in different regions rarely share exactly the same pattern. If the moon formed as an independent body, its fingerprint should reveal that history. The Apollo samples become the test. Powder taken from lunar rocks enters a mass spectrometer. The instrument measures different forms of oxygen with enough precision to distinguish one planetary reservoir from another. Researchers compare the results with rocks from Earth's mantle. The expectation is straightforward. Two different worlds should leave two different signatures. They do not. Within the limits of modern measurement, the oxygen isotope pattern in the lunar samples matches Earth's mantle. The investigation changes immediately. The moon is no longer simply unusual. Its material points back toward Earth itself. That single result does not identify the process that created the moon. It does something equally important. It makes an independent origin increasingly difficult to defend. Evidence significance arrives quietly. The investigation is no longer asking only what the moon is. It is now asking how Earth's own material could have ended up in orbit. One measurement could still be questioned. So researchers looked elsewhere. They examined titanium, then chromium, then silicon. Each chemical system provided an independent comparison. Each was expected to offer another opportunity for the moon to reveal a separate identity. Instead, the comparisons kept returning to the same conclusion. Different elements, different analytical techniques, the same underlying relationship. The moon and Earth's mantle belong to the same geochemical reservoir within extraordinarily small analytical limits. The contradiction becomes impossible to ignore. The familiar picture of the moon as an unrelated companion begins to disappear. In its place stands something much stranger. The rocks collected from the lunar surface carry the same planetary fingerprint as the rocky outer layers of Earth. The moon returns once more. Its appearance has not changed. The gray plains, the bright highlands, the familiar face visible from Earth remain exactly the same. Only its identity has changed. It is no longer behaving like an independent world. It is behaving like preserved terrestrial material. One question now dominates the investigation. If the moon was built from the same material as Earth's mantle, what physical process could possibly lift part of a planet into orbit and leave it there? For decades, there seemed to be no shortage of explanations. Perhaps the moon formed somewhere else and Earth's gravity captured it. Perhaps Earth and the moon grew side by side from the same cloud of material. Perhaps the young Earth spun so rapidly that part of it broke away and became the moon. Each idea appears reasonable when considered on its own. The investigation now has to determine whether any of them can survive the evidence already collected. The capture hypothesis is the most intuitive. Large planets capture smaller bodies throughout the solar system. If Earth could simply pull the Moon into orbit, the case would be solved without invoking anything more dramatic. But orbital mechanics refuse to cooperate. A body as massive as the Moon carries enormous kinetic energy. To become a permanent satellite, that energy must somehow disappear. Without a powerful braking mechanism, the Moon would either continue past Earth or collide with it. The early Earth did not possess enough surrounding gas to slow an object of that size, and no realistic gravitational interaction removes the required energy without destroying the system. The investigation changes. Capture is no longer just chemically unlikely. It is dynamically inadequate. Even if the orbital problem could somehow be overcome, the laboratory evidence would remain. A captured moon should carry the chemical fingerprint of the region where it formed. Instead, its isotopes match Earth's mantle. The first traditional explanation falls away. Attention shifts to the next possibility. Perhaps Earth and the Moon formed together from the same neighborhood of the young solar system. At first glance, that seems to fit the chemistry. If both bodies grew side by side, similar material might naturally produce similar fingerprints. But the Moon's interior refuses to support that picture. A body assembled alongside Earth should contain far more iron than the Moon actually does. Yet every major measurement points to the same conclusion. The Moon is overwhelmingly made of rocky material and contains only a very small metallic core. The investigation changes again. The chemistry appears compatible. The structure does not. The co-accretion model can no longer explain all of the evidence at once. Only one major classical explanation remains. The fission hypothesis proposed that the young Earth once spun so rapidly that part of its outer layers was thrown into space, eventually becoming the Moon. Unlike capture, this idea naturally explains why lunar material resembles Earth's outer rock. For a time, it appeared promising. Then the numbers were tested. To eject enough material, the early Earth would have needed to rotate at a rate far beyond what the present Earth-Moon system preserves. The required angular momentum simply is not there. Modern measurements of the system cannot be reconciled with the extreme spin that the hypothesis demands. The investigation reaches another irreversible point. Capture cannot satisfy the orbital dynamics. Co-accretion cannot explain the Moon's missing iron-rich interior. Fission cannot satisfy the system's angular momentum. 3 different ideas. 3 different tests. 3 different failures. Each collapsed for a different reason. When considered together, they reveal something larger than the failure of individual theories. Every conventional explanation assumes the Moon formed through an ordinary planetary process. The accumulated evidence no longer allows that assumption. The case no longer needs another variation of a familiar idea. It requires an entirely different kind of event. One capable of explaining the chemistry, the internal structure, and the motion of the Earth-Moon system at the same time. The investigation has reached a point where observation alone is no longer enough. Every surviving clue now places demands on whatever explanation comes next. It must produce a moon with very little iron. It must explain why lunar rocks share the same chemical fingerprint as Earth's mantle. It must leave behind the Earth-Moon system we measure today. The question is no longer whether a catastrophic event occurred. The question is whether any physically realistic catastrophe can satisfy all of those conditions at once. Modern planetary scientists do not answer that question by imagining what might have happened. Not as animation. As physics, they build numerical reconstructions that obey the same laws of gravity, momentum, and thermodynamics governing every object in the solar system. If a proposed event violates those laws, the simulation fails. If it reproduces the evidence already collected, it earns its place in the investigation. That distinction matters. What follows is not a recording of the past. It is a reconstruction tested against measurable reality. The simulations begin with a young Earth that has already separated into a dense metallic core surrounded by a rocky mantle. A second planetary body, roughly 1/10 of Earth's mass, approaches on a crossing orbit. Its exact origin remains uncertain. Its role in the reconstruction does not. Researchers vary its speed, its angle, and its size. Most combinations fail. Some destroy too much material. Others produce the wrong orbital motion. Many cannot form a stable moon at all. The investigation changes again. The evidence is no longer eliminating possibilities. It is selecting one. Among thousands of tested conditions, a narrow family of impacts repeatedly reproduces the system we observe today. The incoming body does not strike Earth head-on. It arrives at an oblique angle. Instead of shattering both worlds into countless fragments, the collision transfers enormous energy into their rocky outer layers. The metallic core of the impacting body plunges toward Earth's center. The rocky mantles behave very differently. Immense volumes of silicate rock are superheated. Some melt, some vaporize. Some are blasted outward into orbit around the damaged young planet. The reconstruction has not yet created the moon. It has created something else. A vast ring of incandescent silicate debris surrounding Earth. As the debris expands, it begins to cool. Vapor condenses into molten droplets. Fragments collide. They merge. Over time, the orbiting material gathers into a single growing body. Not an independent planet. Not a captured visitor. A new world assembled from debris already tied to Earth. For the first time in the investigation, the chemistry, the structure, and the orbital dynamics begin pointing toward the same reconstruction. The moon's depleted iron content follows naturally because most of the iron has already sunk into Earth's core. Its Earth-like chemical fingerprint follows because much of the orbiting debris originated from Earth's rocky mantle, with contributions from the destroyed impactor depending on the specific impact model. The Earth-Moon system inherits the angular momentum created during the collision. Independent evidence that previously seemed unrelated now begins to converge. The laboratory measurements no longer stand apart from the orbital calculations. The orbital calculations no longer stand apart from the moon's internal structure. Each supports the others. The reconstruction is not accepted because a simulation looks convincing. It is accepted because multiple, independent observations demand the same class of event. Even so, the investigation does not claim absolute certainty. Researchers continue to debate exactly how much material came from the impacting body, how thoroughly both worlds mixed within the vapor disk, and whether one giant collision or several smaller impacts best produced the modern system. Those questions remain open. The larger conclusion does not. Among all currently tested explanations, a giant planetary collision remains the strongest scientific reconstruction capable of satisfying the evidence collected throughout the case. One final question remains. If Earth endured an impact powerful enough to melt its surface and launch planetary rock into orbit, why does the stable Earth we know today still bear the signature of that catastrophe? The reconstruction appears to end billions of years ago. The evidence does not. In laboratories around the world, researchers can still measure the distance to the moon with extraordinary precision. Small mirrors placed on the lunar surface during the Apollo missions, they simply wait. Every laser pulse sent from Earth turns them back into evidence. Each beam leaves our planet, reaches the moon, and returns in a little over 2 seconds. Those measurements reveal something unexpected. The moon is not fixed in place. It is still moving away from Earth. On average, the distance increases by about 3.8 centimeters every year. The change is small enough to escape everyday notice. Given enough time, it reshapes an entire planetary system. The investigation changes one final time. The giant collision is no longer confined to Earth's distant past. Its consequences are still unfolding today. The explanation lies in the tides. Earth's oceans are constantly pulled by the moon's gravity. But our planet rotates faster than the moon completes an orbit. That slight mismatch drags the tidal bulges ahead of the Earth-Moon line. Gravity responds. The displaced oceans pull gently on the moon, transferring a tiny amount of Earth's rotational energy into the moon's orbit. The result is measurable. Earth's rotation slows. The moon moves farther away. The same process has been operating for billions of years. Evidence preserved in ancient sedimentary rocks supports that long history. Certain fossil tidal deposits record the rhythm of ancient tides and the length of Earth's day. They reveal a planet that once rotated more quickly than it does now, while the moon orbited much closer than it does today. The modern Earth-Moon system is therefore not frozen. It is evolving. The reconstruction that began with planetary violence extends into measurements made today. The consequences reach beyond orbital distance. As the moon settled into its long outward migration, its gravitational influence became an important part of Earth's long-term rotational stability. Studies of the planet's changing axial tilt indicate that the moon helps limit large variations over geological timescales. Researchers continue to investigate exactly how much that stability influenced Earth's history. What the evidence supports is more restrained. The moon contributes to the long-term stability of Earth's rotation. It should not be claimed that the moon alone made Earth habitable. The investigation remains faithful to what the measurements can actually support. One uncertainty has survived since the beginning of the case. Scientists still debate the precise geometry of the impact. They continue refining models of how thoroughly the two planetary mantles mixed after the collision. Some researchers explore whether multiple impacts could reproduce the same evidence. Those questions remain active because science continues testing its strongest reconstruction against new data. They do not erase the convergence already established. Apollo samples. Isotope chemistry. The moon's iron-poor interior. Orbital dynamics. Planetary simulations constrained by physical law. Each began as an independent line of investigation. Each arrived at the same destination more successfully than any competing explanation. The moon returns one final time. Nothing about its appearance has changed. The same gray plains face Earth. The same bright highlands catch the sunlight. The same familiar disk rises above the horizon as it has throughout recorded history. Only the investigation has changed. The object that first appeared to be an ordinary companion now stands as the surviving physical record of Earth's greatest reconstructed transformation. The strongest current scientific evidence does not describe the moon as a world that simply formed beside Earth. It describes it as the enduring remnant of a planetary collision that melted, reshaped, and rebuilt the young Earth more than 4 billion years ago. The moon remains in orbit. The evidence remains with it.